Get started, everyone. Welcome to the last session of the UBC Queen's Intro to Artificial Intelligence for Medical Students workshop. Next year, we will come up with a shorter name, I swear. You know who I am, you know who our facilitators are. Today's session is going to be pretty interesting. We're going to get you to do some hands-on stuff, do a little bit of coding, and try some machine learning out for yourself. That said, without further ado, I'll turn it over to Ricky and Prash.
Okay, welcome everyone. So in this workshop, we're going to actually build a machine learning program in a very similar fashion to how researchers would do it. We're mainly going to use out-of-the-box tools. To get set up, really simple. There's this link here on my screen. Someone let me know if you can't see it, but go to this link. This is a template of the code in Google Colab, which is a nice environment that allows you to Google gives you a programming environment online, so you don't have to install anything. So you go to this link, and go to this link. But first, go File and make a copy in your own drive, because you don't have edit permissions for this specific copy. This is sort of like a master running copy that I'll update. You can go back and look at this version as I update it to reference, but have your own copy so you can type out your own code. Okay, I'll give everyone about 2 minutes to do that. So this code will be in Python, which is, I'd say, probably the most common language used in machine learning right now. And most people, so I'm new to using Google Colab. Last year, we downloaded an actual Python development environment. It took much longer, so this is exciting to me. Anyway, I think the link's also in the chat. So I'll start explaining what we have so far. So Prash set up a lot of narration of what we're going to do in the code, but the meat of the code is not written yet. We're going to do that as we go on. So how this is set up is that there are text-based cells. So when you click around, you see that there are borders around the cell. This represents one block. These are called cells in this Python notebook. There are sections of code that you can run by themselves. So the shortcut to running a block or a cell is Control-Enter. If you run a block of text, it'll just display that block of text. Right. So for instance, if I double click on a cell, that's in editing mode. And if I press Control-Enter, Shift-Enter, it'll execute that code. So in text, it'll just display the text. The text is in a language called Markdown. You don't have to worry about that. Just press Shift-Enter through the text. What you do have to worry about are the blocks that have Python code. So they're the ones that don't have text, like this one. And there's a play button on the left, and this runs the cell as well. So this first block, what we have is, you see a bunch of imports. What we're doing here is that we're bringing in code libraries. So there's existing code developed. So no programmer develops, almost no one develops all the code from scratch, because people have developed tools already that'll help us move along. So there are a lot of libraries we're going to leverage. If this looks intimidating, don't worry. This is very standard practice. You don't need to know these libraries by heart. In standard practice, a programmer will decide what they need and then find the libraries that meet their needs. So here we're mainly using the Scikit-Learn library. This has a lot of machine learning methods in it already, so we don't have to do the math. Okay. In this second section, that's separated by a line break, these are just libraries to help display figures and everything. So pandas is a way to organize data in a nice table. So again, you don't have to memorize this. When I was writing this, all I did was Google search how to display an SVG image in Python, and it says, oh well, use the GraphViz library, so you have to import it. So that's sort of the standard of practice. And this last line is just setting figure sizes so that we have nice big figures. Okay, so if you have any questions along the way, feel free to type in the chat. I might get to it, or even better, Prash might answer it and help you debug or answer any questions that you have. Okay, So now that we understand what this first cell does, we can try running it. So again, Shift Enter. I always thought it was Control Enter, but Shift Enter, and then the cell runs. Okay, and then you see that if it jumps to the next line when you press Shift Enter, that means it ran successfully. Right? If I type something that's illegal code, like I just type some random garbage, it'll give me an error. Okay, so I'll remove the garbage, and then I'll run this block again, Shift Enter, and it runs, and it highlights the next cell. Okay. Okay, if you have any questions, type in the chat. So what we have right here is that this Scikit-Learn library also has a data set embedded to it with breast cancer data. Okay, so the way we load it is with a command called load breast cancer. Okay, but we have to store it in a local variable that we can use. So I'm going to name the variable cancer so that we can use this cancer variable. Okay, so I'm going to load this data set, and then I'm just going to press Shift Enter to make sure it runs. So if it jumps to the next cell, that means it ran. Okay, and then there's a way to, the way it's stored is the data format called dictionary, which means that if I do cancer dot some name of titles in the dictionary, it'll reference that section of the dictionary. So in this specific data set, if you read documentation, there's a section called the keys, which tells you sort of the headings in the dictionary. Okay, sorry about that. So, and you can print them out so you can see what keys there are. So I'm going to print the keys. And then when you say print, Python's going to print something in the output console, which is the blank space that I'm highlighting here. So I'm saying in this dictionary, there are headings. There's the data, there's the target names, desk feature names, and the file name, right? So then in some dictionaries, the description tells us what's in the data set. So I also want to print the description. So I'm going to press Enter to go to the next line and do the exact same thing, except this time I'm going to print the description. Okay. Okay. And it'll give me this block of text. So this describes what the data set is. So it says that, well, this is breast cancer data set from Wisconsin. There's 569 samples. There's 30 attributes, or in other words, features, which is my preferred term. They're attribute features relating to the breast cancer image, like the distance from the center of points on the perimeter, standard deviation of gray values, perimeter area, smoothness, compactness. And then there's also, everything is also divided in classes, whether the outcome is malignant or benign. Right? And there's some summary statistics they nicely give, such as the minimum and the maximum of these features. Okay, so this looks like a great data set. We have 30 features. We have 569 samples. So if you go by the 10 times the number of feature rules, it exceeds that rule of thumb. Again, that's not a hard rule, it's just a rule of thumb, but it's good that we have a lot of samples. And it says 212 malignant, 357 benign, which is great, right? It's not a 50-50 split, but we have lots of malignant and lots of benigns, right? If there's only 10 malignant and 490 benign, that might be a problem, okay? And then all this stuff I don't really care about, okay? References. Okay, so now the first step we usually do in machine learning is something called exploratory data analysis. We want to just get a feel of what the data is. When you're writing journals, sometimes you have to report, I think in biostats they call it a table 1, report the demographics of your data, like how many malignant, how many benign, sort of which patient, how many patients with this perimeter are malignant or benign. So it's always a good way to visualize your data first to get a sense of the range of values. So that's what I'm going to do here. So I want to print the features names to see. I know it says it already in the description. Sometimes there's no description in a data set. So I'll just print it first. And then I'll also print the target names because I want to know what this target means. Okay. So I'll do these two. I'll run these 2 lines of code. This time I'll run 2 lines at once, which is totally fine. And Shift Enter. Oh, I typed something wrong. Okay, it should be an underscore. Okay. So the print function separates each printed statement with a line. So these are the feature names. So there's radius, texture, perimeter, area, smoothness, and then the target is actually what they're calling as the outcome, like malignant or benign. Okay. All right. And then I want to also want to know the sort of dimensions of the data, how many rows and how many columns. So I can do print cancer.data.shape thing, right? Because I think data is one of the key, data is where all these features live. Okay. So run this. So it's 569 and 30. So that makes sense. 569 rows and 30 columns, each column representing one feature. Okay. Okay. So again, as part of exploratory data analysis, there are a lot of techniques. If you search online, exploratory data analysis, machine learning, people say you can do a million things. You can do t-tests, you can visualize it, you can take two variables and visualize it. And that's what we would do. I'm going to pick two random features and visualize it on a 2D plot just to see how they're distributed, right? Of course, you can also do variance, you can do plot it on a distribution, but here I'm just going to visualize it on a 2D plot. Okay, so this first line that's already there, that just sets the size of the figure so it's nice and big for a window. Okay, so the way we do this is we're going to use the plot library, which I named PLT. Plot, well, I want to make a scatter plot. So plot.scatter, cancer, data, and then I'm going to select just, let's say, the first column. So colon means all the rows, comma, 1. So all the rows, but for column 1. I'm going to plot this against all the rows, but column 2. Okay. And then I want to color it. So there's in the plot function, there's a option that you can color your data set by saying C equals, and this will specify how you want to separate the color map. I want to separate it by their target. Okay. Right. So this is what I have. Now, there's some best practices that you can do with this this plot. You can label it. So I'm just going to label it quickly. There's a function within this library called xlabel where you label your x-axis, and I'm going to label it by the title of row 1. Okay, so this looks a bit ambiguous, so I'm taking the column 1 of feature names, and then I have to convert it to a string, which is a file format that's just a bunch of characters instead of numbers. Okay, and I want to do the same with the y label. So I'm going to copy it and just change it to y label, and I'm going to change 1 to 2. Okay. Okay. So we have our mean perimeter plotted against mean texture, right? And then the yellow is the benign and the purple is the malignant. So if we just take a look, and this is also described here in the narration, we can see there's some split here, right? If we just draw a line, for instance, if you do an odds ratio or correlation coefficient, or try to do something with a t-test and get p-values for these variables and then make a scoring system, you're going to create some sort of rule that separates it in a straight line. These are called sort of linear statistics or linear predictors. So the straight line will go through somewhere here, right? And you'll see you'll be able to catch most of it. Your accuracy might be around 80-85%, right? But we want to do better, and we have lots and lots of variables. So how do we do odds ratio with 30 variables, right? Because when we combine them all together, they're in higher dimensions. So we can use machine learning. Right? So to hammer this in further, what we can do, so this is something that's commonly done in biostatistics, is computing the correlation ratios. So what I want to do is I want to take these features and calculate the correlations with each other, see what their correlations are, linear correlations are like. Okay, so annoyingly, there's one obscure step that we have to do, which is we have to convert the dictionary into a data frame, which is like a nice table format to generate these correlations. So I'm going to name this data frame features equals, I'm going to use a pandas library, which I've named pd.dataframe. And then I have to specify data is the cancer data, and the columns would be the feature names. Okay, and this creates that data frame. Okay, and then because the outcomes were in a separate section of the dictionary, I have to create another data frame for the outcomes. So dia outcome, same thing, data frame, data, instead this time, it's gonna be the target section. And then columns equals, I'll name this benign. So because 0 is malignant, I think. Okay. And then I have to merge these two by using a function called concatenate. Df outcome, and then there. Okay. So I didn't memorize this. Right? When I was making this, I needed, like, how do I merge two data frames? You search that on Google, on the documentation, it'll give you this exact example to do. Okay, and now we can compute the correlation matrix. So I'm going to name the correlation matrix core matrix, and then there's a function within the data frame called core, and this calculates the correlation matrix. Right? And I'm going to print this out just so we see what it's like. Okay. Okay, so now I can plot it. So there's a library called SN that gives you a heat map of these matrices. So I'm going to type the code, the line heat map core matrix, and I want the annotations on. And then I want to show this plot. Okay. And then I'm going to run this code. Okay. I typed something wrong. F has to be capitalized in data frame. Okay. Okay. DF one. I typed something wrong again, didn't I? Yeah, I missed an I there. Okay. Also, true is capitalized. Okay, so this is sort of printing the correlation matrix. It doesn't really tell us anything because everything's compacted. So I run this again. It should give me the heat map. So now we see, okay, well, this is ugly. This is really, really small. Okay, so there's a command that we can type to increase the size. Okay, it's matplotlib .rc params figure.fig size equals, and then you specify the length and width. Okay, I'm going to run this again. So shift enter. And then we should have a really nice, beautiful correlation matrix that, you know, your supervisor will love to see this. So this tells us how each variable is correlated with each other. So what you want to do here is, there are two things. One is that you look at variables with either zero correlation or with each other, or something like NaN, which means undefined, which means there's zero variance in one of the variables. So all these variables are nice, they're valid features. And then here, this is the outcome, benign, and then we see the correlation to whether it's benign or not. So we can see that some variables have pretty strong correlation, like the mean perimeter, mean radius, but we know perimeter and radius are highly correlated, right? Some are not, like the symmetry error or with the worst concave points is really good. But then when you just look at this, so what old clinical practice, you take this, you look at the high correlation ratio variables and you make a scoring system. That'll get you about 0.8, 0.85 sensitivity specificity, but we could do better with machine learning. Okay, so this is the entire motivation for machine learning. So this is about all the exploratory data analysis I'll do. You can certainly do a lot more when you look online and see what examples people have. And you might have to do a little bit more if you want to publish something. But this is just to give you a sense of what the data, the sort of the behavior of the data is like. Okay, now we can try some machine learning. So here, I'm going to make a decision tree. Again, decision trees are great because they're very, very intuitive. They're like clinical guidelines. So first thing I have to do is there's a function in Scikit-Learn called train test split. Okay, this helps split your data set into training and testing set easy, so you don't have to do it yourself. Okay, so I have to store it in some variables. So when you look online in documentation, it'll output four values. So I have to create 4 variables for this. And I'm going to name them X train, X test, Y train, Y test. Okay. Again, I didn't memorize this. You look online, if you Google train test split, it'll tell you that it's going to output your training data, test data, your training data, test data. Okay. And then what I need to put inside this function is I have to give it some input. So the input is I have to give it the data, cancer.data. I have to give it the outcome, cancer.target. And then this is the weird thing, we have to suggest a random state. So I'm going to pick 42. Interesting thing, nothing in computer science is truly random. So they have a lot of random user input, or they detect like the temperature of your CPU at some point to generate the randomness. Okay. And then here we're creating empty variables to store the accuracy results, which is already in your template. So this is what's called the max depth here is, I'm just gonna check the chat for any comments. Okay, I think Prash has it handled. Max depth is what's called a hyperparameter. These are parameters that the machine learning algorithm can't optimize by itself. We don't know how to optimize it. It's not discovered yet. So the user specifies this parameter value. In this case, the hyperparameter is a max depth of the tree before it stops generating tree. Okay, so here I'm going to say I want to test a range from 1 to 15 to manually test which one's the best one. Okay, and then I have to loop through all these values. So I do this through something called a for loop. So for, I'm going to name my variable MD and max depth. So it goes through these values and it stores that value in MD. So first it'll test max depth equals 1. Okay, and then we're going to make the decision tree. So in Scikit-Learn, to make the decision tree, it's tree equals decision tree classifier. You have to specify the max depth. Max depth equals MD, and then random state equals 0. You don't have to worry about the random state for now. Okay, and then tree that initializes it. Now we have to fit it to something. So we fit it to X training data. Okay, and then we're going to report our accuracy. 10. So there's a function called tree score that reports the accuracy, but you have to specify of what training data you're using. Okay, and then we're also going to report our testing accuracy. So same thing, test accuracy dot append tree dot score, and then this time we're using the test set. Okay, so that should generate a decision tree and then give us our results. Okay, and then we want to plot it. So here, I'll plot. Again, using the PLT library, plot the max depth against the training accuracy. Okay, and then I'm going to label it. And we'll just do something really simple. Training. Okay, and I'm going to do the exact same thing, plotting the testing accuracy. So here, sorry, I'm just going to copy this line. Max depth, this time I want the test accuracy. Okay, and then I'm going to label it. So the y-axis, and then the x-axis is the max depth. I'm just taking a look at the time. Okay, and from this we want to manually select what the best max depth is. So I'm going to run this. Let's see if I typed anything wrong. Okay, yes I did. I'm missing a colon here. And then I'm also this is a comma, not a period. Okay. Right now I'm missing state. I apologize, I'm making a lot of typos. Okay, there we go. Yeah, thanks, Richard. Okay, so here, this is what we're generating. So this already makes a bunch of decision trees. So this is already doing machine learning. And then we see that best max depth occurs around 3. Okay, so again, if you go too far, it means you're overfitting, you're creating too much complexity that's not going to be able to apply to a test set. So max depth equals 3. So now we want, let's make this decision tree and let's display it. So we have a really satisfying decision tree we can visualize in the end. Okay, so let's make our decision tree, but with max depth equals 3. So exact same thing here. Okay, now I can just copy this code, except max depth I'm gonna set as 3. Okay, so here I'll just type it here, and then I'm gonna reduce this tabbing. Shift backspace usually works. No, it does not work. I do it manually. I don't know the shortcut in Colab. Here. Okay, max depth 3. Okay, and then we want to visualize it. So there's a nice this code. Prash actually found this. Helps us visualize this file really nice. So it's graph. It's already in the template. Just remove the octothorpe or the hash sign, and you'll uncomment that section. Okay, so it'll just plot this decision tree that you generated as a nice graph. Okay, here I'm going to run this section, shift enter again, and then here we got this great decision tree. So here, what do we have? We have our top section. Our top first node, or parent node, which is usually the most important, is mean concave points, and the threshold it set was 0.051. So when you generate a decision tree, you do 2 things. You first select which variables you select, so worst radius, mean texture, and then or mean concave points, and then you select a threshold. Those are the 2 things that decision tree optimizes. So here are the thresholds. Here are the variables. So we see that if you traverse down the decision tree with any patient, you can compare these 3 features, and then you'll have a classification, whether it's malignant or benign. Right? With any patient, their image data, go through this tree, you're going to predict if they're malignant or benign. Okay, and then if you look at the accuracy, what accuracy do you get? Well, you get around 0.9. Well, the training accuracy is higher than text accuracy, which is standard, not always the case. The test accuracy is what we want to look. We have 0.955, so almost 0.96 accuracy. So with this simple decision tree, we are performing much better than if we just use linear correlations. And again, the clinicians love this method because it's so intuitive. You look at it, you say like, okay, we're gonna take a patient, we're gonna first evaluate their mean concave points, then their worst radius, then their mean textures, then their samples, right? It's like evaluating whether they have a sore throat, what their fever temperature is, and number of lymph nodes in lymphadenopathy. So this is a really intuitive machine learning method. It's not always the best, but this is a nice example that you can use in your practice in your own personal projects. This next section looks at the feature importances, which isn't, I'm going to skip for now. I'll show you the code after. It's just plotting. There's just a one-liner that you can select which feature is the most important. But in decision trees, it's the one in the parent node because that gives you the most, splits up the most data and gives you the most information. So mean concave points is the most important feature. And this also motivates further studies. Like, what does mean concave points mean? Well, work with pathology, get a tissue sample out, and then analyze it, and then bam, you have another paper out. Okay. So before we move on to Prash's section on more advanced techniques, if there are any questions, feel free to type in the chat. Otherwise, I will let Prash take over, and he'll show you some other aspects of machine learning.
Thanks. Just going to catch up with you on the code. Okay, I hope you guys can see all of this. So I'm working on the same notebook that Ricky was on, so you can see that as he added his code in here, I have the same results as he does, which is great. If we have time at the end, like Ricky said, we'll look at feature importance and we'll plot some of the, we'll plot what the decision tree learned, and we can visualize why it's important. If there are any questions, of course, just type them in the chat or speak out, and someone will answer it. So after decision trees, we are now going to look at logistic regression to see if we can use logistic regression to classify the tumor data into benign and malignant, and how accurate that is compared to decision trees. Now, if you remember, logistic regression for one feature looks something like this. This is a sigmoid curve, and it will define a curve which you can then threshold into your malignant and benign samples. And if you remember, logistic regression can only define linearly separable decision boundaries, which means that if you had a 2D plot, it can only really draw a straight line between your features to classify. And although in one dimension, this might not be very useful. So if you remember from this plot at the very top, if you drew a straight line to try and separate the data, you can see that for these two features, mean texture and mean perimeter, it's not super helpful. And you might, even though you'll catch most of it, you'll still miss quite a few. But if you did this for all 30 features and then combine the output, we might have a better chance of capturing the distribution of the data. So I'll show you how to do that using Scikit-Learn. It's quite simple. It's very similar to how the decision tree was trained. So the first thing is to define the logistic regression classifier. So as Ricky mentioned, there's nothing here that you need to memorize. Everything is a simple Google. So if you didn't know how to do what I'm going to type now, you would just have to Google how to do logistic regression in Scikit-Learn, and there will definitely be like hundreds of websites telling you how to do that exactly. So I'm going to call my classifier logreg for short, and then use logistic regression. This is the Scikit-Learn class. And I'm going to define the maximum number of iterations to be 5,000. And I'm just going to fix random state to 1, just so that if you do this in your own browsers and you use these exact same numbers, you can reproduce the code exactly. So once you've defined the classifier, you need to fit it to your training data. So Ricky already split that earlier, so we can directly access it right now. So if I hit Shift Enter or Control Enter, it will run it. And as you can see, it then prints out that classifier and the different properties of that classifier. So right now we've trained it, but we don't know how well it's done. So we can print the training and test errors. So that's quite simple. We can use a print function, type in training error. So everything in these quotes is just a string that I've defined. So this is, I could change this to anything and it will just print it directly. This is not a variable, it's just a hard-coded string. And if we use a comma, we can combine different types of strings together to be printed. So now I can type in my classifier, the score, and the score on the training set. So now if I run this cell again, you'll see that it tells me the training error is about 96.2%. Now I can do the same for the test error. Just copy and paste, change this to test, change these to test as well. If you highlight something, this is a cool shortcut. If you highlight something and then press Control D or Command D, it will select the next sort of pattern that it matches. So here I can now edit two words at the same time, which saves a lot of time if you have a ton of different variables or words to edit. And now if I hit Control Enter again, it will print the test error. So you can see that it actually performs logistic regression, even though it's linearly separating these features, it's able to get 96.5% accuracy, which I believe is quite similar to the decision tree. So this suggests that the features, or at least some of them, are separable enough that you can get really good accuracy with a linear classifier like logistic regression. And so here, if you do this and you see really good accuracy, this is a huge clue that you don't need to use more complex methods like neural networks. But for the sake of this tutorial, we are going to cover that just so you can see how to do that for your own projects. Great. So now, even though we sort of know what the errors are like for the training set and test set, it would be nice to see what the confusion matrix looks like, or what exactly the classifier is classifying as malignant and benign, and what that means in terms of the true positive and false positives. Now, this is another great biostat thing. You always see these confusion matrices, and you can derive all kinds of different accuracy metrics from this. So I'm going to show you how to do that in Scikit-Learn as well. It's super simple because this is just another built-in function that you can easily access. So the top line here, I'm defining the initial figure and axes, and I'm just saying that it needs to be, I think it's 10 by 8 inches. So to get the confusion matrix for your logistic regression classifier, you just use the plot confusion matrix function. If you hit tab when this kind of tooltip pops up, it will just autocomplete for you. And now I can, oh yeah, this is another tip. So when you when this kind of when you're typing a function and this hint pops up, it will tell you the different inputs that this function will take. So estimator is the classifier that you used. So I want to use our logistic regression classifier. If I hit comma again, it will bring up the next thing. So then it will tell you your input data and stuff. So this is really there to help you remember what goes into this function. So once again, you don't ever need to memorize anything. So I want to see how the logistic regression classifier performed on the test set. So I'm going to enter the test set details. I'm going to include the labels as well. And remember, Ricky said that the way they had coded it was that 0 was malignant and benign was 1. So that's the order I'm going to put it into. And I'm also going to use a blue color map just for the sake of it looking nice. So it's as simple as that. And then I'm going to use the show command to show the figure. And now when I hit Control Enter, hopefully it will show, yeah, it shows the confusion matrix. Now the font's a little bit small to see, but hopefully you can tell that this logistic regression classifier, when looking at the test set, was able to correctly classify 51 of the malignant tumors as malignant and 87 of the benign tumors as benign. And the false positive and false negative rates are quite small. So the false positive, it inaccurately predicted 2 tumors as malignant, even though they were benign. And false negative, it inaccurately predicted 3 tumors as benign when they were actually malignant. And if you combine these numbers together, you will see that you'll get a test error of 96.5%. So it's really that simple to train logistic regression. And as you'll see in the next couple of cells, it's just as simple to train a neural network to do this kind of classification. Are there any questions before I move to the next step? Okay. So doing a neural network. If you remember, I said that since our logistic regression accuracy is quite high already, usually a neural network is overkill. Oops. But for the sake of demonstration, I'm going to show you how to do that using Scikit-Learn. And you will see that it does improve accuracy a tiny bit, but whether that's meaningful or not is really up to you to decide for your own projects. So for today's example, we're going to train a simple, fully connected neural network. Now, if you remember from our previous session, a fully connected neural network essentially means that each layer, the nodes in each layer are connected to all of the nodes in the next layer and the previous layer. So this is the input layer here. Now, I don't expect you to count them, but there are 30 of them here, and they represent each of the features that are in this data set. And for this particular example, we're going to use 2 hidden layers with 5 and 2 neurons each. So this is the first hidden layer, which has 5 neurons. And you can see that each of the neurons is connected to each of the 30 neurons before and connected to each of the 2 neurons afterwards. This is the second hidden layer, which has 2 neurons. And then finally, the output layer, which will output one number encoding whether it thinks that particular tumor is benign or malignant. So making something like this in Python is super easy. Just going to show it here. So once again, just like with logistic regression, you have to define a neural net classifier. Now in Scikit-Learn, this is called a Mlp classifier, which stands for multi-layered perceptron, because back in the day when these kinds of neural networks were first introduced, each neuron was actually called a perceptron. So this is a multi-layered perceptron network. So to do that, I will call my neural network neural net, and then you use the Mlp classifier function, brackets, and then we'll show you the hint. So what I'm going to do is, here, let's copy this over here. I'm going to use the Atom optimizer to optimize this neural network. Now, this is one of the most common optimization techniques to use, and I almost always recommend you use this one. So don't worry about it. So these are just some of the other hyperparameters that you want to set. You'll notice as you play along with these different parameters, if you change them too much, your neural network will stop performing well. And that's something for you to play around with to see how neural networks are quite sensitive. Now, the next parameter that I'm going to set are the hidden layer sizes. So I already said that we're going to use 2 hidden layers with 5 neurons in the first one and 2 neurons in the second one. So that's as simple as just saying hidden layer sizes equals 5, 2. And I could make it totally different. Like I could keep adding numbers here to add layers to the neural network. But for now, we're just going to stick to a simple one. I'm going to use a maximum iteration of 1,000. I'm going to set this to false so it doesn't print too much output. And then I'm just going to fix the random state to 1. So this defines our neural network classifier. Now, in addition to the classifier, I'm also going to use something called a scalar or a transform. And this usually helps neural networks train more stably. And this is essentially just normalizing each feature so that it has a mean of 0 and a standard deviation of 1. And when you do this, not just for neural networks, but also other classifiers like logistic regression, you will notice that it generally improves the performance by a little bit. For the previous classifiers, it wasn't really necessary, but for this, it will help. So to do that, it's really simple again. You access the Scikit-Learn function, standard scalar. This is known as standardization, but it's essentially just, as I mentioned, it's transforming the input data to have a mean of 0 and a standard deviation of 1. So you want to fit it to your training data. And then once you've defined this scalar and fitted it, so I'm going to hit Control-Enter to do that. You can then transform your training data to the scale data by using the scalar variable. So now you can do this. And then the same for the test data. So this new scale data will be representing the same features as before, but they've just been scaled. Now you have this data, you can fit your neural network to that scale data. So just like before, you have your neural net classifier, and then you use the fit function. And it's as simple as that. If you hit Control-Enter, it will train the neural network. And here it just prints out the different properties of that neural network classifier. Right now, we don't know how it's doing, so let's just print the errors to figure it out. Same as before, training error, and using the score function. And I'm going to copy this line. and we look at the test error. Okay, hit Control Enter. Great, so you can see that the neural network actually outperforms logistic regression and I think the decision tree as well. And now the accuracy is on the test set 98.6% as opposed to 96.5 for logistic regression. What does that actually mean on the data? So we're going to plot the confusion matrix again for the neural network to see what difference that made. So down here, it's almost the same. In fact, I can just copy and paste it from earlier and show you. Just change this to neural net. This can be changed to the scale data. And then just for difference, I'm going to use a red color map instead. So now this is the confusion matrix for, this is the confusion matrix for the neural network. So you can see that the false positives and false negatives have actually gone down to 1 each. And before, remember, this was like 3 and 2. So that is what is causing the accuracy to go up to 98.6%. So clearly neural networks do help a little bit because they can learn nonlinear patterns. And in this data set, that makes a tiny bit of a difference. Yeah, that's the end of both the logistic regression and neural network examples. Are there any questions? If not, we can go over the feature importance cells. Let me take a look at the chat. Nope. Okay. Ricky, do you prefer going over the feature importance, or do you want me to do it? I'm okay either way.
Doesn't matter. How about you? You can go since your screen's already shared.
Okay, sure. Yeah. Okay, so if you remember, we decided that a max depth of 3 was the best for the decision tree because it led to the highest test error without overfitting. So we're just going to look at in this decision tree which were the most important features. Now you can visually tell from this flowchart itself that clearly that mean concave points and these next few features were clearly important in defining the decision tree, but we can look at the exact importances as well. So I'll just show you how to do that here. So for accessing the feature importances, we just need to use the feature importances attribute in the decision tree. So we can print it directly here. So when you print and you use a string with these curly braces here, you're essentially saying to put the value of some variable in here, which you're going to define later. So this is kind of just like a placeholder saying that some value is going to go in here. So this is just an alternative way of printing what I was printing earlier. So to do this, you use the period and then format, and then you can do tree feature importances. So now if I run this cell, we can see that, sorry, I don't need this part. We can see that you can see that this is a 30, it's a list with 30 different numbers in it representing each of the features, and each of the numbers represents the importance of each feature. So you can clearly see that there's only a few of these features that are non-zero, which means there are only a few of them which are important. We can better represent that using a bar chart to look at which features these numbers represent. So we can get the length of the features by doing this. Oops. This just tells you the length of the columns in the data, so we expect that to be 30. Define our figure again. And now we're going to use a bar chart. So we're going to do so from the 30 features, assign them each to their feature importances. And then we're going to give it some labels as well so we can interpret the graph a bit better. So these are just giving the ticks on the y-axis. We can give an x-axis label as well. And finally show the figure. So now, instead of just getting a list of numbers telling you different importances, we can directly plot that for each of the features. So clearly we can see the most important or the most helpful feature in defining whether a tumor is benign or malignant is the mean number of concave points. And that's no surprise given that was the top leaf or the top node in this decision tree. And then you can see the next most helpful features are the worst texture and worst radius. Now we can go a step further and actually plot plot the features against each other to see why they're or how they're helpful. So if you remember from earlier in the scatter plot, we found that there's quite a bit of like overlap between the mean texture and mean perimeter, so we couldn't really classify them easily. But it turns out that these features are more helpful. So we can do the same thing, except this time we can plot the mean concave points against the worst radius, for example. So I'm just going to do that here to see what that looks like. So the worst radius and the mean concave points, I did already sort of put it here as 7 and 20. So we can do just define these as parameters. And use a scatter plot again. So instead of now typing in 7, because I've already defined it earlier, I can just use mean concave points. And this is good because you can change these numbers to whatever you want, and then you just run this once and plot different features. And I will show you an example of that just after I finish typing this out. So this is exactly the same syntax as before that Ricky described when he was doing the scatter plot. And then once again, I'll just do the x-axis and y-axis. Hopefully there are no errors in here, but now when I run this, yeah. So here you can see that plotting the mean concave points against the worst radius gives us a much better way to separate the tumors. So here now, if we drew a line or somehow separated them, we'd catch way more of the cases than before. And this is what leads to the high accuracy that we saw in the decision tree. Now, we can do the same thing and look at the least important features as well. So we could just pick any two of these which are 0 and see how that looks. So for example, we could do the mean smoothness and the mean compactness. So all you have to do is change these two numbers to whatever columns that the mean smoothness and the mean compactness are from in the original data set. So I know that those are 4 and 5. And if I just run this cell again and look at the plot, we can see that it's much more overlapping. It's actually very sort of near impossible to distinguish the tumors based on these two features. And that's why they don't really appear in the decision tree as important features. Yeah, so that was feature importance. And this is kind of like doing exploratory data analysis after you've trained your classifier to kind of understand what's going on and why these features are important or not important. And that's also an important step to do to try and interpret your results. Yeah, so that's actually pretty good timing. It's almost 7. Let me know if you have any questions. And at the end of the session, we'll share, if you weren't following along and if you didn't code this in real time, we'll share the final notebook with you with all the code in place so you can run it in your own time. You're welcome.
Great. How's about we end up there, guys? Because it seems like there's no questions. Yeah, cool.
Sounds good.
All right, everyone. Well, thank you for joining us for this session and all the sessions beforehand. Hopefully you learned some key facts about the fundamentals around AI. A big thank you to Ricky and Prash for facilitating the last several sessions. And thank you, the participants, for which this would be possible. There is a post-workshop survey that will be sent out. Please, please, please submit it. It helps us improve this workshop for our next offering next term. If you liked it, tell your friends. We will be doing this again. Ricky, Prash, any last words?
Yeah, well, I hope everyone got something out of this. I know AI is coming really fast. It's really exciting, and everyone here is interested in it, and we're very happy that you're able to come. So thank you all for attending this workshop.
Yeah, thanks everyone. And please do fill out that workshop, that post-workshop survey. That'll really help us know what to change or what to keep for next time.
Awesome.
Right.
With that in mind, good night across the country.
Thanks everyone.